Welcome to Algorush. Today, we're going to pull back the curtain on some of the world's most powerful databases to meet the invisible workers who keep everything running smoothly. Yeah, we're talking about the unseen janitors of your data.
Okay, so let's just dive right in with a big question. We all want our apps and services to be lightning fast, right? And modern data systems are absolutely amazing at saving new information in the blink of an eye. But how do they actually do it? And maybe more importantly, what's the hidden price we're paying for that incredible speed?
You see, to understand the clever tricks they use, we first have to get a handle on the problem they're trying to solve. And this isn't really a problem with code, it's about the hard, physical reality of how computers actually store stuff. It really all comes down to a fundamental bottleneck, especially with older spinning hard drives. Think of it like a record player. If you want to jump the needle to random songs all over the vinyl, it's slow, it's clunky. That's your random access. But once that needle is in a groove, just letting it play through is super smooth and fast. That's sequential access. And this physical limitation is the dragon that database engineers have had to figure out how to slay for decades. Here's a perfect way to picture it in your head. Imagine you need to jot down a bunch of ideas fast. What's the quickest way? You just grab a bunch of little slips of paper, scribble one idea on each, and just toss them on your desk. It's super fast, it's easy, and you don't have to waste any time stopping to organize anything. So, this is where engineers had a really ingenious idea. They asked, what if? What if we never had to do those slow, random updates at all? What if we could design the entire system to work just like that messy desk? And here's how they pulled it off, using a technique often found in something called a log-structured merge tree, or an LSM tree. First, every piece of new data, every single update, every new record, it doesn't go straight to the disk. It goes into a super fast table that lives in the computer's memory. Then, once that memory table is full, the system takes that whole chunk of data, sorts it all nice and neat, and writes it to the disk as one brand new sequential file. And here's the key. That file will never be changed again. It's immutable.
So, this is the big aha moment. We've completely sidestepped the original problem. We took all of those slow, painful, random writes and transformed them into a non-stop stream of incredibly fast sequential writes. It's a brilliant solution. But, like any clever solution, it creates a whole new kind of problem.
Right. So, by solving the write speed problem, we've basically created a cleanup problem. Our fast and easy approach has an unintended consequence. Our nice digital desk is about to get really, really messy. See, every single time that memory table fills up and gets flushed, we create another one of these little files on the disk. They're often called SS tables, which stands for sorted string tables. And you get one, and then another, and another. And pretty soon, you don't just have one big data file, you have hundreds, maybe even thousands of these little sorted files all just piling up. Now think about it. What happens when you need to find one specific piece of information? You don't know which of those thousands of little paper slips it's on. The system has to check the newest file, then the one before that, and the one before that. All of a sudden, reading your data, which is supposed to be fast, has become incredibly slow. This exact problem has a name, and it's kind of the new villain of our story, read amplification. It's this idea that one simple question from you, like find this user's profile, forces the database to do way more work behind the scenes, performing dozens or hundreds of read operations just to track down the answer. So how in the world do we fix this digital mess? Well, we need a cleanup crew. We need a process that can work quietly in the background, constantly tidying up our desk. And that process, really the unsung hero of modern databases, is called compaction. Compaction is basically our janitor. It's this background job that comes along, scoops up a whole bunch of those small, messy files, and merges them all together into a single, bigger, and more organized file. And while it's doing that, it gets to throw out all the old, outdated, or deleted data. It's literally like taking all those little sticky notes and organizing them into one clean, consolidated binder. Now, there are a couple of popular ways to do this cleanup. The first big strategy is called leveled compaction. You can think of it as organizing data into different tiers or levels. All the brand new small files land in level 0. Then, as compaction runs, it merges them and promotes them into bigger, more organized files at level 1. And then those get merged into level 2, and so on. Data essentially graduates through the system, getting more organized as it goes. So the huge advantage of leveled compaction, it keeps the total number of files you have to check really, really low, and that is fantastic for read performance.
To find something, you pretty much only have to check one file per level. But what's the downside? Well, you're constantly rewriting data as it moves between the levels. This creates something called write amplification, where the same piece of data gets written to the disk over and over again. It's a classic engineering trade-off. The other main strategy is a bit simpler. It's called size-tiered compaction. And instead of having all these strict levels, it just looks for groups of files that are about the same size, like a few 10-megabyte files, and it merges them all together into a new, bigger file. Okay, so let's put them side by side. Leveled compaction, which you'll find in systems like RocksDB, is awesome for workloads where you're reading data way more often than you're writing it, because it keeps that digital mess to an absolute minimum. But it pays for that tidiness with more background writing. On the other hand, size-tiered, used in systems like Cassandra, is better for write-heavy workloads because it does less rewriting, but at the cost of having more files to check when you need to read something.
And this brings us to the big finish, really the core lesson of designing any high-performance system. There's no magic bullet, there's no perfect solution, and there is definitely no free lunch. Everything is a trade-off.
In fact, you could say that every single choice these engineers make is just a constant balancing act between three competing forces. Three types of amplification that are always in a giant tug of war with each other. This really lays out that three-way tension perfectly. You've got read amplification, how many files you check for one query. Write amplification, how many times you rewrite the same piece of data. And space amplification, how much extra disk space you use for old versions of data. If you tune your system to minimize one of them, you almost always make one of the others worse. You simply can't win on all three fronts. You just have to choose which battle you're willing to lose to win the war. So what's the real bottom line here? The goal is never to find the single best compaction strategy, because it doesn't exist. The goal is to deeply understand what your application needs. Do you read more or do you write more? And then choose the right strategy and the right trade-offs for that specific job. Which kind of leaves us with one final thought for you. If you were building the next big thing, what would you choose? Would you sacrifice the lifespan of your disks just to get lightning-fast reads for your users? Or would you be okay with slightly slower queries in order to handle a massive, non-stop flood of incoming data? There's no single right answer,